Okay, let's dive into this. Today, we're going to pull back the curtain on an invisible force that powers so much of our modern world. Seriously, it's a fundamental process happening all around us, from the batteries in our phones to the shiny chrome on a classic car. We're talking about something called redox. I mean, have you ever really thought about it? How do you get a perfect mirror finish layer of one metal to stick so perfectly onto another? Or what about this? How does a simple coating stop a massive steel structure from just crumbling into rust? Well, the answer to both is the same, and it's this beautiful little bit of chemical choreography. The secret, the real magic here, is a process called a redox reaction. And yeah, I know, it sounds a little technical, but at its heart, it's just a simple, elegant exchange. Think of it as the invisible engine driving all sorts of stuff. And today, we're going to pop the hood and see exactly how this thing works. And this right here is the core idea. A redox reaction is not a solo act. It's a duet. You've got two things happening at the exact same time, and you literally can't have one without the other. One partner gives an electron away, and the other one has to accept it. They are perfectly in sync, always. So let's break that down. It's actually incredibly simple. Oxidation is a loss of electrons. Reduction is a gain of electrons. So if a substance loses electrons, we say it's been oxidized. If it gains them, it's been reduced. That's it. That's the entire dance, in just 2 steps. So in this chemical dance, each partner has a very specific role. First up, you've got the oxidizing agent. You can think of this one as the electron thief. Its job is to cause oxidation by swiping an electron from its partner. But here's the twist. By gaining that electron, the oxidizing agent actually gets reduced. It's a little bit of a paradox, I know, but it's totally key to the whole process. And of course, the other partner is the reducing agent. This one's the generous electron donor. It gives its electrons away, which in turn causes its partner to be reduced. And naturally, by losing an electron, the reducing agent itself gets oxidized. See? It's this perfect self-contained loop where one action directly causes the other. Now, knowing about this dance is one thing, but how do scientists and engineers actually control it? How do they measure it with any kind of precision? Well, that's where this really powerful technique called redox titration comes into play. It's how they manage this electron exchange with incredible accuracy. And it's not just one single method. There's a whole family of these techniques, and they're usually named after the specific chemical, the titrant, that's used to control the reaction. Now, while they all look a bit different, the two you're going to see most often in labs are iodometry and permanganometry. These are the real workhorses of applied redox chemistry. Okay, so we're controlling an invisible exchange of electrons. That brings up a pretty big question, right? How do you know what's happening? How can a chemist see the reaction as it's unfolding to know when it's perfectly balanced? They need a way to track the progress. And the answer is by measuring something called redox potential. The easiest way to think about it is like a pH meter, which measures acidity. Well, a redox potential meter measures a chemical's tendency to gain or lose electrons at any given moment. By tracking this one value, you can basically watch the entire reaction happen in real time. So we have this amazing measurement tool, but what's the logic behind it? How does that potential number connect back to the actual chemicals swirling around in the flask? What's the rulebook that governs this whole process? Well, this is the rulebook, the Nernst equation. And I know what you're thinking. That looks complicated. But don't worry, stick with me. We're not going to do any math here. The only thing you need to know is that this equation is like a brilliant bridge. It connects the abstract idea of reaction potential to real measurable things in the lab, like temperature and how much chemical you have. Let's just peek under the hood for a second. E is the potential we're trying to measure. The other letters stand for things like a baseline starting point, the temperature, and a couple of physical constants. But the most important part for our story is N. That little guy represents the actual number of electrons being traded in the dance. The key takeaway is that this equation proves the reaction's potential isn't random. It's directly tied to the physical conditions and the number of electrons flying around. So when chemists track that potential while they're adding their titrant, they can plot the results on a graph. And what you get is this beautiful, dramatic S-shaped curve. And this curve isn't just a bunch of data points. It's a visual story. It tells you everything about the chemical dance, from the very beginning to the very end. Let's just walk through the story it tells. It starts out slow. Then it enters this steady buffering region where things are changing gradually. But then, bam, you hit the equivalence point. Look at that sharp, almost vertical jump.
That's the climax of the reaction. It's the exact moment where the electron donors and the electron acceptors are in perfect balance. This steep climb is the big signal chemists are looking for. After that, the reaction is done, and the curve just flattens out.
Okay, so all this theory about curves and equations is fascinating, but here's where it gets really important. Why does mastering this even matter? Because controlling this reaction is what lets us build and protect the world around us. Let's connect it all back to those real-world examples we started with. This precise control over redox reactions is a huge cornerstone of modern industry. I mean, think about it. The silicon in your computer's microchip had to be purified using redox. The shiny, protective chrome on that classic car, plated using a controlled redox reaction. Even the coating that stops a massive steel bridge from rusting into the river is a direct application of this science. It's happening everywhere, quietly building and protecting our world.
So, we've gone on quite a journey, haven't we? From a simple question about a car bumper all the way down to the invisible dance of electrons and the tools chemists use to choreograph it. And really, it all comes down to one powerful idea. So here's the bottom line, the one big takeaway. Redox isn't just some concept in a chemistry textbook. It's a fundamental transaction of nature. And by mastering techniques like titration, we've learned how to measure and control this electron exchange with incredible precision. And that control, it's like a superpower. It gives us the ability to create new materials, build stronger stuff, and protect it all from the elements.
It really makes you wonder, doesn't it? We've learned to choreograph this invisible dance of atoms with incredible precision, all just by tracking the flow of electrons. It really begs the question, what's next? I mean, from photosynthesis in a leaf to the firing of neurons in our own brain, nature is full of other, much more complex electron exchanges. What will it mean for us when we learn to control those too?